everyone, and welcome back to JNB Tutorials. So today we have a video on momentum and impulse, and the focus is on change in momentum. So the first video covered what momentum is, and we looked at some examples. Okay, so at the end of the video we covered a simple scenario but did not expand on it. So now we're going to take it from there, and let's just get right into it. So we said imagine there's a soccer ball which is just lying there at rest, and that soccer ball is suddenly kicked and it moves to the right at a velocity of 5 meters per second. Assume the mass of the ball to be 0.5 kg. Calculate the momentum while it is at rest and the momentum when it moves away. Okay, so this is a scenario that is going to showcase change in momentum changing. Okay, so let us just get right into the calculation. So initially it's at rest, we can calculate the initial momentum. Okay, so the initial momentum, we're going to express that as Pi, or P initial. So this will be m times v initial, or m times the initial velocity. But the initial velocity in this case is 0. Therefore, what would be our P initial? Our P initial would be 0 as well. And then we go on to the final momentum. So after the kick, it moves away and then it has a certain momentum. Okay, so this, we're going to say it's P final, or PF. This is the momentum when it's now moving away. So this is going to then become 0.5 multiplied by 5 kg. Okay, and this gives us 2.5 kg meters per second to the right. So this is the momentum after it has been kicked. So now that we have the initial momentum and the final momentum, this leads us directly to calculating what we can now call a change in momentum. So the change in momentum is going to be something that is expressed as the difference between the final momentum and the initial momentum. Okay, so we're going to say change in momentum is equal to PF minus PI. So PF is also equal to MVF, right? And PI is equal to MVI, right? So we can see that the mass is common in both sides, and then as a result we can express change in momentum as M times open bracket VF minus VI close bracket. So this is how you can essentially express the change in momentum of an object. Okay, so let's now express the change in momentum for this one. Firstly, we're going to have to deal with direction. We have to state which direction is positive. So in our case, we said let right be positive. Okay, so if right is positive, we're going to have delta P is equals to PF minus PI. Okay, and as a result, we substitute, we have 2.5 minus 0, which gives us 2.5 kg meters per second. And just like momentum, change in momentum is a vector, so the direction is towards the right. I have other examples that you will look at, and this will make it easier for you to understand this concept more in depth. But let us now go to scenarios that are likely to occur. So there are scenarios that are likely to occur for us to calculate change in momentum. So firstly, an object can start or stop. Okay, so if it starts from rest, it can be that example of the soccer ball that we've just covered. or it can actually bounce off or suddenly change direction. Imagine a tennis ball hitting a tennis racket and then going back or going back to the center. Okay. The third one is an object becoming faster or becoming slower. A case would be maybe a car, it's accelerating, or the driver is hitting his brakes. So those are the likely scenarios that you can have that might actually want us to calculate the change in momentum. Let us cover two examples and then we go on to the second sub concept. Let us have a look at the first question. So let me just read it out. A car traveling east at 60 meters per second suddenly decreases its velocity and continues at a slower velocity of 40 meters per second. The mass of the car is 1000 kgs. Calculate the initial momentum, the final momentum, and the change in momentum. Okay, so here I've written down the information that we were given a mass of 1000 kgs, initial velocity of 60 meters per second to the east, and a final velocity of 40 meters per second still to the east. So we require to calculate the initial momentum, final one, and the change. So firstly, we're going to do the important thing. We're going to say let east be positive. Okay, so we let it be positive and then we can continue with our calculation. So for the initial momentum, we're going to say m times vi, which is going to be equal to the mass, which is 1000 multiplied by 60 meters per second. This gives us how much? 60,000 kg meters per second. Okay, and this is east. And then we go to the final momentum. This is the second part. So we're going to say m times vf. And here the mass is still 1000, but the velocity has now decreased to 40. So have 40,000 kg meters per second. And this is still to the east. So this is how easy you calculate the initial momentum and the final momentum. And then for the change in momentum is equals to pf minus pi, which you can say is equals to mvf minus vi. Okay, so it's possible to use this equation to calculate, but since we've already calculated this and this, we can just use this, right? Okay, so what's our initial momentum? It's 40,000 kg meters per second minus the initial momentum, which is this one. Okay, 60,000 kg meters per second. What's our solution? So this gives you negative 20,000 kg meters per second. Now what does this negative tell us? It tells us the direction. So if east is positive, this would mean west is negative, right? So we're going to say the change in momentum is equals to 20,000 kg meters per second west. Okay, so we've just calculated everything that they wanted from us here. Okay, so let us go to the second question. So the second question reads as follows. A sportsman of mass 70 kgs runs at 12 meters per second to the east. He reaches the end of the field and turns back to the west at a velocity of 7 meters per second. Calculate the change in momentum. Okay, so with this one, you are going straight to calculating change in momentum. You're not calculating the initial one, not calculating the final one. So we know the formula for change in momentum is what? Change in momentum is equals to pf minus pi, which we can express as m vf minus vi. Okay, so before we can get on with our calculation, let's just get some other things straight. So this initial velocity is to the east, and this one is to the west. Okay, and then let's indicate directions. So we're going to say let east be positive, or let direction to the east be positive. Okay, and then once we have done this, now we can continue with solving or answering their question. So we're going to say delta P is equal to mvf minus vi. Okay, let's substitute. Mass, we have 70 kgs. The final velocity is which one? It's this one. And it's 7 meters per second to the west. If it's to the west, that would mean that it is negative. So we're going to have negative 7 minus, what's the initial velocity? It's this one, 12 meters per second. So it's minus 12. So you're going to have 70 minus 19. And then you punch this in the calculator, you're going to have minus 1,330. Okay, this is kg meters per second. So we have a negative here. What does this indicate? It indicates direction. So we're going to say delta P is 1,330 kg meters per second to the west. Okay, and then we are done. So what if this was positive? So if we had found this value as positive, that would mean that our change in momentum is to the east. Okay, so now as we continue, we're going to be looking at Newton's second law in terms of momentum, or in relation to momentum. So one can ask themselves this question. We saw a change in momentum, right? But what actually caused this change in momentum? And a potential answer to this is the object could have interacted with something that exerted a force on it, bringing about the change in the object's state of motion. You see, imagine a tennis ball hitting a tennis racket. So when it hits the tennis racket exerts a force on it as it exerts that a force also on the tennis racket. So that is how Newton's second law then comes into the picture. Or we can say a certain force was applied that resulted in a change in momentum. You see, so that's how Newton's second law then applies to momentum. Okay, now let us now define this Newton's second law, but in terms of momentum. So you used to define it plainly based on force, mass and acceleration. But let us now define it in terms of Newton's second law, in terms of momentum. Okay, so this is how we're going to define it. We are going to say the net force acting on an object is equal to the rate of change of momentum of the object in the direction of the net force. Let me read it again. The net force acting on an object is equal to the rate of change of momentum of the object in the direction of the net force. And this can quickly be taken and be put and be made into an equation, because as you can see, this definition allows us to quickly put it into the equation. So they say it's a rate of change of momentum. Rate of what? Change of momentum. So when we talk about rate, time has to be involved in a way. Okay, so we're going to say F net, which we knew to be equal to MA according to grade 11, is now equals to delta P all over delta T. Okay, in the next video we'll look at how this equation came about. Okay, and look at how it actually was derived, because it has a mathematical derivation. So we also say that delta t is usually a very small time interval, and the net force is constant over that time interval. Okay, and the change in momentum is in the direction of the net force. So if the force is going to the right, therefore the change in momentum is also to the right. Okay, when we start with the next video, we directly going to derive the formula, and then we expand on it and look at examples. So make sure that you actually go to the video and look at it. Bye for now.